Okay, we have one more example that we'll do today. But I first want to make a couple of statements. I'm not going to write it on the board. But we've now seen already that every polynomial is continuous. And remember what continuous means? It means it's continuous at every point on its domain. And if P and Q are both polynomials, P over Q is continuous everywhere except where the denominator is 0, except where Q of x would give you a 0. Well, now let's move to a trig function. Theorem. Sine x is continuous, which means it's continuous at every point on the real line. Let's take a look at the proof. Well, in order to prove it's continuous everywhere, we first just take any arbitrary point. Let x naught be an element of R. We'll prove it's continuous there. Since x naught was chosen arbitrarily, we will have proven the theorem. Okay, to prove sine x is continuous at x naught, well, just like every other continuity proof, let epsilon greater than 0 be given. And as usual, if you want to choose a delta, I'll frequently try epsilon and see what happens. And in this case, it worked. So we're going to choose delta equal to epsilon. Thus, if x minus x naught is less than delta, we have the following. And what do I have to prove that sine x is continuous at x naught? Well, I have to prove that sine x minus sine x naught is less than epsilon. So we're going to do a little bit of algebra, a few trig identities that you probably don't remember and I don't have memorized. So this is equal to 2 cos x plus x naught over 2, cosine, sine x naught minus x. Did I do that right? X naught. Yeah, I'll write them. I'll be consistent. I wrote x plus x naught. It's the same thing, but I'm going to put x naught plus x, and this will be x naught minus x over 2. And I'm just going to write justification, a trig identity. Okay. Now let me just write it this way. It's equal to 2 times cos x naught plus x over 2 sine x naught minus x over 2. That's just the property of absolute values. I broke it into 3. I pulled the positive 2 out and then put each one of those into an absolute value on its own. Okay, well this is less than or equal to 2. What's a nice limit, upper bound for cosine, period? A nice upper bound for cosine. Yeah, it's never greater than 1, right? That's 1. This here is always less than or equal to 1. Well, I'm going to go ahead and write times x naught minus x over 2. And I'll explain why. I'm just going to write by the justification, sine of z is always less than or equal to z. This is another trig identity. All right, and if you think about it, absolute value looks like this. The absolute value of sine, instead of going above the x-axis, below the x-axis, above the x-axis, absolute value is just going to go hump, 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 like that. So it's going to be like that. Well, what's this equal to? X naught minus x. And we know that it's less than delta, but that happens to be equal to epsilon. So we're done. One final comment. No proof. But a theorem, cosine x is continuous, and you basically use the fact that cosine x is equal to sine of pi over 2 minus x. That's just another trig identity. Okay, so now we've established that sine and cosine are both continuous, and we'll continue with that next time.